So I want to discuss a few more of these homework problems that you are supposed to do tonight. So that will give you a little bit of a picture of what's going on. Some of it is algebra, so we won't go too much into detail. And then I will switch to, for the last module, I want to go over some issues in causality, which are going to be very different from analytics in general. It's going to be more, you will see one particular place where machine learning and data analytics comes in, but for the most part it's more statistical and philosophical in trying to understand how do you differentiate between associativeness and causality. Okay, before we broke for lunch, we saw basically these neighborhood methods. So the code is available to you. This time around it's a MATLAB code, not a Python code. One exercise that you could do is basically take that MATLAB code and write it into Python so that it gives you an idea of how things can work there. I started doing it, but then didn't have enough time to run this. Another one, write a computer program to determine the page rank of a system of websites. Run your code on the figure 14.7 from HDF with epsilon equal to 0.5. Does the resulting page rank vector make sense? Know that the page rank is only unique if the associated Markov chain is irreducible. Rerun your code for different values of epsilon. Does the page rank vector respond in the way you should expect it to? So let's just run this code so we have some ideas of what it is. And again, as I said, you should be able to, for some reason MATLAB keeps dying on my computer, which is another reason that one should run away from MATLAB to Python. It never dies, or at least I'm hoping. I'm just hoping that there's nobody from MathWorks here. Okay, good. So this is basically the PageRank algorithm. Mu is equal to PageRank Q and epsilon. You give the matrix Q, and it constructs inside it a new transition matrix, which is 1 minus epsilon times the Q that you give, and epsilon over D times 1 transpose. It's going to try to get the eigenvalues, eigenvector decomposition of Q, and tries to find the real eigenvalue which is closest to 1. We know that the eigenvector corresponding to the eigenvalue equal to 1 is going to be the stationary distribution, and that is how we are computing the stationary distribution here. We are basically looking for the identity of the eigenvalues whose real part is closest to 1. In actuality, if this is a probability transition matrix, there exists an eigenvalue which is exactly equal to 1. But in order to make sure that no numerical issues are coming up, and that had to come with the fact that the matrix Q, after all of those multiplications, may not turn out to be exactly symmetrical, in which case the eigenvalues may not exactly turn out to be right. So to control for that, we are looking for the minimum of the absolute error. And then you basically take here, take the eigenvector corresponding to that eigenvalue. Now the eigenvector from the eigenvector decomposition would have norm equal to 1. This time around we don't want the norm to be equal 1, but we want the sum, which is the L1 norm of this eigenvector to be equal to 1. So we just normalize by the sum. That's what returns the value. And this is the question, this is the one that generates the value for the standard, for values, that's Q matrix up there is the transition matrix corresponding to that figure. When you run this code, it will generate the stationary distribution for all values of epsilon starting from epsilon equal to 0.01 to 1. Okay, and let's run this, and let's look at this mu sub c vector and see what it happens. So let's say, let's start with the last one. So the last column over here, which is basically, okay, let's say that if epsilon is equal to 1, let's go back and look at our story over there. I want to sort of see what it does. So here's my So this was how I'm going to correct. So this Q bar matrix is what in the code I'm calling Qi. It takes 1 minus epsilon times the correct Q that has been estimated and adds to it this epsilon correction. When epsilon is equal to 1, what do you expect should be the importance of the various nodes? When epsilon is equal to 1, what is happening? Every time, so remember the interpretation that we have at the bottom. Where is my pointer gone? Oh, here it is. Not 0, but close enough. Maybe not 0. Now so here's the thing. In this Markov chain, we randomly click on a link with probability 1 minus epsilon and randomly choose a new web page from the entire universe of web page with probability epsilon. So if epsilon is equal to 1, what are we doing in this corresponding Markov chain? We are randomly picking a particular website. Next time we randomly pick another website. The next time we randomly pick a third website and keep going. So what should happen if this notion of importance makes sense, then what should happen to the importance of the various sites? Is any site more important than any other site? No, all the sites should be basically the same because you're randomly picking a site and then going to the next one and picking a site and so on. So there shouldn't be, all the websites should be equally ranked. Okay? If they're equally ranked, what should be the stationary vector? Uniform. And in this particular case, there are 6 websites that were there in the example. I think, let me see what the, so there are 6 different websites that are given. Page 1, this is the date, this is a small network over which things are happening. And as a result, what do you think would be the stationary distribution? 1/6, right? And that's exactly what you get. 0.1667 is nothing but 1/6. As you make epsilon smaller, you should start to see more and more importance coming from the distribution itself. So at the smallest value of epsilon, let's try to see, let me see if I can make this window a little bit smaller so we can compare it to our figure and see whether this actually picked up something interesting. So let's see if I can get both of these guys to sit next to each other. So that's the stationary distribution that we found. So the highest weight went to page 1, the next highest weight went to page 3, then to page 2, and page 4, 5, 6 are very small. So looking at this, does that seem about right? So page number 3 has the highest page rank. Page number 1 is comparable, and 2 is the next one, and then after that is everything else is negligible. So in some sense, why do you think that these guys, so 6 and 4, these are going to be, 6 and 4 are going to be very small. Why? Incoming links are not there at all, which means why do we even have this non-zero? Why do we even, see, if there is no incoming links, page 4 and page 6 should never be visited. So why does it even have an importance? Where is that coming from? What? But where is our random part? What is the one? The epsilon. So if the epsilon, now as I increase epsilon, intuitively what should happen to page 4 and page 6? Their weight should keep on increasing. So let's see whether that actually happens. So keep just looking at page 4 and page 6. They went on increasing as compared to where they started from. And they start dragging weight away from 1, 2 and 3, which are the highest ones. And 1 and 3 have a lot of incoming, outgoing, there is a lot of connection going on. And can we argue that why should 2 have a lower than 3? Maybe just by the edge count? 2, so 3 has the most number of edges there. 1 has sort of the next level and 2 has the next level. So that's how these ranking turns out. So intuitively it seems to be making sense compared to what the picture is. So this is just a simple example of what to do. You guys can play around with it also and try to see what you can get out of that. The other, where did my solutions go here? The other piece, this is a very complicated solution, forget it. I don't really want to look at it right now. Let me look at the assignment itself so I can tell you what the next piece is, and before we go down to something else. Okay, the next problem that is of interest is this missing data problem, which is a nice problem. This is taken from Barber. And actually in the break somebody was asking what's a good book. I would suggest Barber's book is actually a pretty good one. It's available online for dimension reduction. You can get a lot of examples. You just search for Barber and machine learning, you will get it. And here what we are trying to do is solve this missing data formulation problem, where xij is the data that I have. I want to write it as a combination of b times z. And here gamma ji is equal to 1 if xji is available and it's 0 otherwise. So from there I can now write a coordinate descent algorithm. You optimize over z for a fixed b, and that's actually, so if I fix the value of b and optimize over z, what kind of an optimization problem is this? From a purely optimization perspective, is that an easy optimization problem? If I fix b and optimize over z, it's quadratic. It's basically a linear regression problem. It's a mean square error problem. If I fix b and solve for z, it's a mean square problem. If I fix z and solve for b, again it's a easy problem. So you can try to do this coordinate descent. Now b and z together, it's a non-convex problem. Together that optimization problem is not going to work. And so you can try to do coordinate ascent or coordinate descent in this particular case. So optimize z for a fixed b, coordinate b for a fixed z. So what will happen, it may be that system is underdetermined. If the system is underdetermined, how do I solve that problem? What would be an easy way to fix that problem? So what's happening here is I am claiming that if you look at this problem, it might be that when you try to minimization and set up this fixed order or first order conditions and try to solve them, you don't have enough equations. So how would I like to modify this problem so that that never happens? What would be a nice way to take this regression problem or regression like problem so that you never have this issue of underdetermined? So remember we were talking about another formulation. Would the underdetermined story happen in regression as well? Can it happen in regression? If you have too many factors and too few data points, what will happen to the equations for beta? Sorry? Forget about the variance, you may not be able to solve it even, right? So what do people do in practice to fix that problem? Ridge regression. What you could do a feature selection, but suppose you can't do feature selection, then one way to just regularize the problem is to do a ridge. You put a ridge term which will always make sure that things are invertible. So in order to fix this problem, you should try a ridge, which is you separately penalize the norm of b and norm of z, and that will make sure that this thing will always be regularized. Put a small number lambda, that will make sure that this will always have the right number of equations and solve it. And in general, regularization is a good idea per se. And then you can write a program which iterates between a and b until it converges. And that's an exercise that you can try out. It's very simple. It's an actual, and there is data available in Barber's book that you can play around with. The last two problems that are here are actually more theoretical in nature, and the solution is there, you can take a look at it, but for my purposes I just want you to remember the results, and I've mentioned this, the second result already in the notes. This result is also worth knowing, that if you take x is a random vector, it's a d-dimensional vector with a variance covariance matrix sigma. If you take the eigenvector decomposition of this covariance matrix sigma, and let's say gamma I is the eigenvector corresponding to the ith largest eigenvalue lambda, then this gamma I has a very nice representation. it's the vector that picks out the largest variance among all dimensions which are orthogonal to the first I minus 1 eigenvectors. So the first eigenvector of a covariance matrix picks out the direction of the largest variance. So if you look at a covariance matrix and you look at what happens to the term x transpose sigma x and look at the level sets, it might look something like that. So the first eigenvector picks up this direction because that's the largest variance area. The second eigenvector will be in a direction which is orthogonal to the first one and picks up the largest variance in that direction. It will pick up this one as the next one. And I've done a 2D picture, so it's done. But if there was ND, what this result shows is that the next eigenvector is going to pick up the direction which is orthogonal to the first two and has the highest variance. So in some sense, not in some sense, in exactly, these eigenvectors are trying to pick out the directions that explain the highest variability. And this is why when we were doing this PCA, we found that pretty quickly about 150 eigenvectors were explaining most of the variance because they are greedily trying to pick up the direction of the highest variance, and that's something to keep in mind. That's good, but there's also another thing to keep in mind is that if you're okay, let me show you the picture that's to keep in. There's a eigenvectors also have this other story that I want you to look at, which we did in PCA, and this is a picture that I want you to keep in mind as well. This one. So remember yesterday we emphasized the fact that taking the PCA or an eigenvector of a matrix should not be a brain dead exercise. You should look to see what is the matrix that you're looking for. So if you have two classes and you want to discriminate between them, and if you decide that, let's say that I first do a PCA and I'll then do the classification. So this is a two-dimensional data. So let's say we become greedy and say that let's just take the first PCA, reduce the dimension to 1, and then I will do the classification. If you did PCA on this, which direction will it pick? Actually the photograph, I mean the caption here tells you the direction that it will pick will be actually this magenta direction, because that is the direction that explains most of the variability of the combined data. But that's utterly useless for doing any classification. When you project all the data points on this direction, you get nothing. So you need to depend. So when you're mixing PCA with classification, you have to be careful. Sometimes it works, sometimes it doesn't work. In the example that we showed in class today, we took these faces, we did a PCA of the faces directly, and then we did classification on them, and it worked fine enough. But there is no guarantee that that should work when you project these faces down on the 150 dimensions, maybe everything gets confused. So you've got to be a little bit careful about how you do the PCAs. PCA without any class labels tries to find the highest variability directions. Sometimes it's good, sometimes it causes problems, and that's something to keep in mind. The second problem is something that we already discussed in class, where we're saying that in this exercise we will show that the R rank SVD is the one that minimizes this error for when the rank of M is exactly equal to R. And in fact, if you make it less than equal to R, it will be the same thing, where dr is constructed from D by keeping just the first R singular values. And we assume that X, D, and okay, it doesn't really matter. This particular construction exactly shows you how you end up getting that, and the solution is there. It's more for your knowledge rather than necessarily in terms of practical implications. This has very little if you believe that the SVD result is true. If you want to work out and how to get the result, it's over there. What was the other example that I wanted to show from here? This is another example. This is the movie database that you worked with assignment 5. In particular, you have the missing elements. You can use the same code that we had for the recommendation system, and instead of looking at test set and where did it go? Here. this one, this collaborative filtering idea where we were using to recommend movies. We can use a very similar idea to even fill up the rankings of a matrix. And that's the last exercise. So play around with that. That will also be there in the solutions, and you should get a good understanding of what's going on there. Now what I want to do is switch gears and talk about causality. And that's a different a very different mindset. So this has been taken, there's a book by Wasserman and there's a book by Gelman and Hill. So the chapter 16 and 17 from Wasserman and chapter 9 and 10 from Gelman Hill are good references to look at. This is a fairly, I'm going to try to go slow through this, try to understand it because it's important. If you have questions, please feel free to ask because it's something that's going to, well, this is part of a different course, so it was a disclaimer made that the paper that the students were supposed to read were not going to be there on the exam. Okay. So causality is based almost all the time that we are talking about machine learning. In a sense, we want causality. Those are the typical questions that we may want to ask. Does a Facebook ad make a person buy the product? And buy how much? Which design of an ad is better to attract customers? A/B testing. I show them two different designs and I ask, is this better than that? So the question that we want to ask is, does a treatment, so most of the causality literature actually was gotten from biostatistics or from medical statistics, where the treatment literally was a treatment. You have two groups of people. One of them you give placebo and the other one you give a drug, and you want to see what the difference between them is. And so that's why the word treatment comes in. So you want to look to see whether a treatment T causes the outcome Y. And really what I want to differentiate between is T causes Y or T is associated or correlated with Y. These are two different questions, and differentiating between these things are actually very important, because if T is correlated with Y, it is possible that there exists some other cause which is impacting both T and Y, which is actually called a confounding variable. That can cause trouble. Whereas if T causes Y, then by looking at this, by perturbing values of T, you want to look at what perturbation happens to the values of Y. Just an aside, I don't know whether many of you saw this. There's an interesting report that has come out that placebo actually might be a true effect. That is, if you tell the mind that you're being given a medicine, somehow seems to treat itself. So this is not just psychological, physically it seems to treat itself. There is a nice article in the New York Times that appeared last week. It's worth just reading about it. Okay, going back to our story, here we are going to assume that the placebo does nothing. Okay, so what I want to think about is the following situation. Suppose Y and T are related via a linear model. I want to do linear regression, and suppose the prediction of Y using T is given by Y bar equals beta 0 plus beta 1 T. Okay, I built a linear model of this sort. Now if I have this linear model, I want to differentiate between how this linear model happens in various machine learning setup and what this linear model would suggest in a causation setup. If I say that T causes Y and the relationship is in this manner, what I mean is that if I take a same unit, I take a person and give them a certain level, let's take for the moment, let's assume T takes only values 0 and 1. Either I give them the treatment or I don't give them the treatment. If I give them the treatment, the impact should be beta 0 plus beta 1. If I don't give them the treatment, the impact should be beta 0. The causal inference is about comparison for the same unit. It's response to different levels of T. The big issue is for each unit we have the response for only one treatment. So let's go back to this drug testing model. If I want to say that a treatment helps individual X, then for individual X I have to first not give them the treatment and see what happens. then give them the treatment and see what happens. And if I have this for all people, give them the treatment, not give them the treatment, and then I fix a regression model on that, you will end up getting a causation model. But in most setup of causation, what happens is that each person either falls into the treatment set such that t is equal to 1 for this person, or they fall into the non-treatment set where t is equal to 0. So the corresponding point for this person is always missing. Either you always get a no treatment sample, or you always get a treatment sample. So this is when you're talking about causation, there is a huge missing data problem. I mean, this is like a matrix completion problem. You want to be able to impute for each person what would have happened had they been in the other condition. All right? We don't have that data. So 50% of the data is missing. That is a huge amount of missing data. And therefore, finding causation is actually a difficult exercise. And increasingly, what people are trying to do is trying to get towards the end of this. I'm hoping that I'll get to that end point. We will see how machine learning is starting to help in this process of identifying this missing data problem. So once we think about causation or estimating causal responses as a problem in solving missing data, we can start thinking about using machine learning techniques to try to, or data analytics techniques to try to fill in that missing data. In general, when we are regression, we are talking about predictive inference is about comparison between units. You have n data points, you want to predict the outcome for the n plus 1th data point. You're not predicting what will happen to the same data point in two different conditions. We are trying to predict in the next data point, if I give them in one condition, what is going to happen. So causation is about between units, causal is in the same unit. When you write this model, you cannot differentiate between them. What it comes down to is, when you write this model, how do you use them? Typically, we are using them between units and we don't worry about causation. All right. So here what I want to do is start making things a little bit formal. So let's say that there is a single binary treatment. It takes value 0 or 1, and there are n different individuals in my population. Let's assume that the population is homogeneous. The population does not differentiate in terms of they're all basically the same. If they are not given a treatment, then the random response of the population will be referred to as C0. So let's say that you're not given, you're ill with a particular disease and you do not get any treatment. There is a randomness at what happens to the progression of your disease. Some people will progress very aggressively, some people may not progress at all, and some other people might recover from it. So there is a randomness associated with that. That corresponds to C0. If you're given the treatment, then the same population has a random component which is C1. And when I'm trying to figure out what is happening, I want to look at the difference between these two. You want to estimate the expected value of C1 minus the expected value of C0. This is what I'm after when I'm talking about whether the treatment helps. If mu is positive with enough confidence, we say that that treatment is helpful. Easy to estimate if samples of both C1i and C0i are available for all units I. But we only either have C1i or we have C0i. So this is what is going to happen. So now let's think about, when we do the treatment, what do? The measured response of somebody is yi is equal to C1i, meaning it's a sample from the C1 distribution if ti is equal to 1. If this individual got put into the treatment group, that means its corresponding treatment variable was 1, then the sample that I got was a sample from C1. If this individual was put into the no treatment group, then the sample that I got was C0. But the counterfactual C0i was missing in this case, and the counterfactual C1i was missing in this case. What would happen to this unit if they had not received the treatment is not available, and similarly what would have happened to this unit had they received the treatment is not available. So the only samples of one of the two possible outcomes are there. Okay, so what do I do now? This is something that I can estimate. I can estimate the conditional expectation of y given that t was equal to 1 minus the conditional expectation of y given that t is equal to 0. Let's call this association. And the whole causal inference problem is trying to figure out when is mu equal to alpha. Mu, look at the difference between the two. Here I'm looking at the expectation of C1, here minus C0. Here I'm looking at the expectation of y, which is C1 if ti is equal to 1, minus the expectation of y when t is equal to 0, which is C0. Now, it looks as if this should be very similar to that. And we will, I'll give you a counter example in a moment where things will go bad. But before we get there, let's try to intuitively understand when can things go wrong. Can you think of a situation where mu and alpha can be different? Because it almost seems that there is nothing dramatic going on. So let's take this drug testing situation, right? We are doing a randomized trial. I want to try a new drug in the market, and I want to see the efficacy of it. And so I'm signing up people for randomized trials. I'll put some people into the condition where they get the treatment, some people I put into the condition that they don't get the treatment. Now, hypothetically, think of yourself as a patient who's almost terminal, and there is an experimental drug in the market. What are you likely to go and tell your physician? Please sign me up. I am about to die otherwise. Maybe this drug is going to help me. Sign me up. And if you are somebody relatively healthy and you think that your disease hasn't progressed too much, and the doctor says, well, do you want to try this experimental drug? What is your response going to be? No. So now, if you look at this condition, there is an unknown factor, which is healthiness. If the healthiness is bad, you are likely to be in the treatment setting. If the healthiness is good, you are likely to be in the no treatment setting. So when you look at the responses of people, of the people who receive the treatment, even if the treatment is good, it's likely to be biased low, because the people who entered this treatment already were in a very bad state. So let's say that you were in a terrible state, the treatment pulled you up. The other side, people were generally okay. And so you might think that even though there was a huge bump that came from the treatment, when you look at the, where did it go? I'm going too far. Okay. When you look at alpha, alpha might turn out to be negative even when mu is positive. That is, if I give, all things being equal, if I give you the treatment, you improve. But the problem is, when I do this sampling, if the t variable that I am choosing, the whether or not I give the treatment to the person, if it's chosen in such a way that somehow their outcome is going to be correlated with some variable that is also correlated with the way they are put into the treatment program, you end up having problems. And in most of these causation versus correlation story, something of this sort is happening, meaning that there is an unknown variable that is affecting both C, the outcome, and T, which is how I put them into the different categories. And I'll show you a very simple example to bring this down. So the association versus causation. Suppose that you have 2n patients. Okay? N of them will receive the treatment and n of them are going to be control. It's the same name, meaning that they do not receive the treatment. That's called the control group. The causal effect that I'm looking for is a change in the health condition due to the treatment. So how would you estimate mu? Yi be the health condition of the ith patient after treatment. Ti equal to 1 if the ith patient received treatment and is equal to 0. You estimate mu hat I to be doesn't like me to be near my computer. Okay. So here I'm taking the variable ti, so it's the summation of yi ti over ti, summation of ti. Here it's the summation of yi times 1 minus ti over the summation of 1 minus ti. This is just a fancy way of saying take the average over all the people who received the treatment, average over all the people who did not receive the treatment. This is how I want to estimate mu hat, but what could be the problem? So think about the in some sites. So suppose the true, and this is, I don't remember the exact reference, but it's a very fascinating case, which at the end of it I'll tell you why this is fascinating. Suppose there is the true unknown causal effect, mu is equal to 0. This treatment is completely useless. It doesn't make any difference to anybody. And suppose and this is just building out the example that we were talking about. Suppose 2n individuals are there. The n individuals are in good health before x is equal to 1, and n individuals are in poor health before x is equal to 0. And x is called a confounding variate because it predicts the outcome y. The people who are in good health, when you measure their health afterwards, are likely to have a higher score for good health. People who are in bad health to begin with are likely to have a bad health outcome later on, whether or not they are giving the treatment, because the treatment behind the scene, which I don't know, the treatment has no effect. Suppose 2/3 of patients with x is equal to 1 get assigned to the treatment condition. And so in this particular case, think of treatment as a new vitamin routine, and it's going to enhance your health outcomes. And people are told sign up. So those people who are very health conscious are more likely to sign up for this than other people who are less health conscious or health unaware. So 2/3 of the patients who are very health conscious end up into the treatment condition. 2/3 of the patients who were not health conscious end up in the control condition. Now keep track of the reds and blues, because reds will stand for x equals 1, blues will stand for x equals 0 in these slides. Treatment has no effect, so y is equal to x, meaning after the treatment, the health effect after the treatment is exactly equal to the health effect before the treatment. Now if I try to estimate the causal effect, what is going to happen? I'm going to take the total health of the people that were in the treatment condition, that is 2/3 of the good health people, 1/3 of the bad health people, and divide by n, because this is the average of the people who got the treatment. This is the average of the people who did not get the treatment. Okay? Because 2/3 of the people good people were here, 1/3 of the good people were here, if you look at the difference between them, you end up getting that mu hat is 1/3. Meaning, in fact, you would estimate that the treatment helped. If I don't do anything corrective, I would conclude that the treatment helped. So what went wrong? Clearly we already know what went wrong. The assignment of people to the treatment condition or the control condition was confounded by this variable x that also determined what the outcome is going to be. So if that happens, we run into trouble. And that's something that one should always keep in mind. Now this, I'm blanking on the reference, but it's a fascinating result. This actually happened. So there was a miracle drug of some sort, or a miracle vitamin of some sort, where sports associated people did sign themselves up. People who did the study didn't account for this confounding effect. They published something that this has a great effect on your health. The people who were in the treatment group knew nothing happened, right? Because they were health conscious people, they looked at their health, nothing happened. People who were in the condition where they did not get this drug felt cheated and said, maybe we should get this. And so, but it gets worse. Everyone in the control group hears about the fact that mu hat is greater than 0 and switches. Now ones on the treatment group know that T does not change their health, so they stop taking the drug. You run another set of studies, so performance after the switch, 2/3 of the bad people now are taking the drug, 2/3 of the good people are now not taking the drug, and now if you did this problem, you get mu hat equal to minus 1/3. So suddenly the result of the causal result before forces people into the opposite direction, and you get a causal result which is negative. This is not hypothetical, this has actually happened in practice. This is something that happens, I would argue that perhaps in all of these various health supplements that are coming out, this kind of a story is probably happening on a routine basis. So what we want now is some theory that lets us get figuring out how to solve this problem. Okay, let's think about this example. How could I have solved this case? And we will fix it as we will give a more mathematically rigorous way of dealing with it. But suppose we got into this problem. I have 2 N individuals. I need to figure out what to happen to treatment. What would I have done? And let's say that I have some way of measuring their health also. I know that N of them has good health and N of them have bad health. And let's say that I do a testing to make sure what their health condition is, and somehow I'm able to figure out exactly what their health condition is. So what should I have done in order to fix this problem? Weighted. Match them? No, but there is an easier solution, right? In this case, I don't even have to match them. What would have solved my problem?
I would have allocated them having the same number of, the proportion of the health quality level in one group should be.
Exactly. So in this particular case, because there are only 2 possibilities, I should have, with 50% probability, put a healthy one into treatment versus no treatment, and an unhealthy one into treatment versus no treatment. So I should have unraveled something. I should have found this variable x, which potentially has something that could be correlated with my output, which is the health condition. So I have the initial health condition potentially is correlated with the final health condition. So when I put them into the treatment, I should have randomly put down people. Okay, suppose these conditions were 4 of them, not 2. What would I have done then? I would have had to go through this exercise of trying to divide all 4 conditions equally in the 2 conditions. Now, most people's health condition is not a discrete level but a continuum. So now I have this problem of how do I assign things in a continuous fashion between conditions. In this particular case, there were only 2 treatments possible, 1 and 0. But what if there were many different treatments I could give? I am trying to design a website, and I have 5 different designs that are possible. And I want to do the same thing. I want to figure out whether investing more in my design actually increases traffic to my website. What could be the confounding factors there? If I want to look at the traffic coming in, what do I want to measure? So I want to show them one of these 5 different designs, right? What confounding factors do I have to worry about such that if I after the fact tell me design number 3 is the best, I don't run into this problem? Are there things that one might have to worry about? Platform. There's also another problem, right? Like if this website is a banking website versus let's say it's an entertainment website, would the factors change? Would the confounding factors change?
You are associated with the bank only, then you are the customer.
One of the customers, and even if you give me a pretty bad website, I will somehow struggle through because I have to get that work done. Entertainment website, I will go away. So you have to sort of also, if for example you end up showing for a banking website that the improved website does not change traffic in any significant way, that doesn't mean that actually there wasn't a causal effect, but there was a confounding factor that people would have worked with whatever website you give them because they have to get some work done out of it. So you have to be a little bit careful about how exactly to do it. So we'll build up to that. Okay. Suppose here's a math example, and then we'll get into the problem there. Suppose the treatment and control assignment T is independent of C1 and C0. Healthy outcomes, unhealthy outcomes. In our little example, T was not independent because if you were healthy, you were 2/3 more likely to be put into the treatment group. If you were unhealthy, you were 2/3 likely that you were put into the no treatment group. So suppose this was independent, then what happens? So the causal effect is going to be the expected value of C1 minus the expected value of C0. This is by definition what I'm after. I want the expected value of what happens to my health after treatment minus to what happens to my health after no treatment or being in control. Now what happened? How did I go from there to there? This is just mathematics. How do I go from, why can I claim that this line is exactly equal to that line? What is the property that I used? Independence. The conditional distribution of C1 given T is the same as the unconditional distribution of C1, because I'm assuming that T is independent of C1. In fact, T is independent of the pair C1 C0, therefore T is independent of C1. Similarly over here, T is independent of, when you look at T conditional distribution of C1 given that T is equal to 1 is the same as the one before. Similarly, conditional distribution of C0 given T is equal to 0 is the same. What happened in the next line? The next line, what I'm saying is that if T is equal to 1, then all the samples that I'm getting Y are exactly equal to the sample of C1. If T is equal to 0, then the samples that I'm getting in the no treatment condition are exactly the same as the samples of C0. Therefore here I end up getting that once I condition on T, this line is exactly equal to that and that one is exactly equal to that. This difference is exactly alpha, which is association. So causal effect is equal to association. Suppose the probability of T equal to 1 and the probability of T is equal to 0 is positive, then this quantity is an unbiased estimator of mu. So how do you get confidence intervals on this mu? You can basically use the same kind of bootstrapping idea, or you end up getting, you can subsample from your population and start getting compute confidence intervals on mu. Is the independence assumption violated by the example? Yes. The same situation when T equal to 1 given x is equal to 1 is equal to T is equal to 0 given x is equal to 0 is 2/3. So therefore here the conditional distribution of T1 does depend, unconditional distribution of T1 is a half, because a half people got treatment and a half people got no treatment. So therefore the unconditional distribution of T1 equals 1 is a half, but the conditional distribution of T1 given x is equal to 1 is 2/3. So here there was a dependence between treatment and the underlying variable, which is health, and therefore we didn't end up getting the causal effect that we wanted. Again, the same story. If you have treatment conditions with random outcomes C, T goes from 1 to tau, there are tau different treatment conditions. T in this is a random mapping of units to treatment conditions. Suppose T is independent of all the outcomes that you can potentially get, then you have the same result, that if you take a sample approximation of what happens, you end up getting a good approximation for what happens to the treatment condition. And here you're essentially taking the same story. IA denotes the indicator function of event A. So now what we have gotten ourselves into is that we need the treatment to be independent. Often this is difficult, so we'll have to think about what to do. All right, random assignment is often not possible or cumbersome. So take our example of this health case. We are saying that if I wanted to get the causal effect, what I really want to do is be able to first check their health condition, then randomly assign them to two conditions. Think about the case where somebody wants to get this what shall we say, a health supplement. They may or may not want to subject themselves to a health checkup. So sometimes trying to find this random effect is not possible or difficult. So we go back a little bit lower and we want to still get that independence, but not overall independence. And so let's take the following situation. We'll say that a treatment condition T, the way I assign people to treatment conditions is ignorable. This is a new technique, new term that I'm putting in. If the following things happen, that T is conditionally independent of C given some confounding variables X. So what does that mean? So suppose X will be age cohort, gender, education level. Suppose these are the variables that defines a particular individual. We will say that T is independent of the outcome y1 and y0 for each value of x that belongs to this. This does not imply that t is independent of these two treatments. This is a well-known paradox called the Simpsons Paradox, and in fact currently this Simpsons Paradox has been showing up in educational setting a lot, and it has to do with the fact that when people are trying to, in many educational institutions in India, abroad, everywhere, people are trying to figure out whether there is a fair representation of students in their educational program which is representative of the underlying population of these people. And people argue that if take any program, if the representation is far away from the population, it turns out that they declare that this is not going to be a fair allocation. But one of the things that often gets into a problem is that the number of people applying to these programs are often very different. And that comes down to this, because in a way you can sort of think about assigning people to educational programs is also an assignment problem, and we want to argue whether, given their intrinsic abilities, are they being placed into these programs with equal probability. And when you test that, there is a very nice paper by people in Berkeley which brings out the Simpsons Paradox in education. But there's also very many studies that have been done in the United States about incarceration, and people have found that African Americans, Latino Americans, and other minority groups are overrepresented in prison populations. And the argument being made there is that this definitely means that things are unfair. And in some ways, the data has come to show that given the conditions, this may not be unfair, and one of the places where they go for justification is Simpsons Paradox. Okay, go back to this story. What we are saying now is, I have subdivided the population, and in the subdivided population, the people going into the treatment group and the no treatment group are equally probable. At the overall population level, this may not be possible, but in the subpopulation, I have been able to do this. So the causal effect, which is, say, the result for the teeth level of the treatment, now what we are doing is we are writing that these lines are math. So in this particular case, I'm writing the expectation as it is, and then I'm writing that take the expectation of the conditional expectation of the treatment given x, which is the age, cohort, gender, education level, etc. So what you do is, first, for any given value of x, compute out what is the conditional response of the treatment, and then take the expectation over all possible groups. So why is this true? Why is this line true? Again, this is just pure mathematics. This is nothing to do with causality. What is happening over here? Is this always true? So what is going on here? What is this expectation over? What is this? This outer expectation is over what? Over what variable? X or C? X, perfect. The inner one is a conditional expectation of C given X. The outer one is an expectation over X. So is this anything special happening here? Is this true only because X happens to be this particular variable? Or could X have been anything and this was true? Anything. So this is just probability theory. You can do anything you feel like it. It's always true. What about this line? Now I'm taking the expectation of t equals t and x. Again, is there anything special happening over here? No. Same story, it's just probability theory. Okay, now what happened from here to there? Now I'm using the fact that from here, if I go from, okay, there are two different things going on over here. Let me actually make it very clear. Actually, I must take it back. I went a little too quickly. So The first one is expectation of, I'm going to write it in a special way. And this is an expectation over x here. So you read this line with the outer one with an expectation with x. This is always true. So this line is always true regardless of whatever you do with it. The next line, there is a subtlety involved. The next line, I could have written it in this form. So if I write it in this form, where I condition on both t and x, and I take the expectation over t and x, this is always true. Okay, but this is not what I'm doing in the second line. In the second line, I'm taking expectation with respect to x, expectation of ct, t equal to just a particular value of t, and x. So I just wanted to make it clear that I went a little too quickly on that line. If I take the expectation over t and x and take the conditional distribution of ct given t and x, then this is always true. This is just probability theory. In this one, what I'm doing is I'm conditioning only on one particular value of the random variable t, not all possible values of the random variable t, and I'm not taking the expectation over there in this line. There's only two expectations. This is for just a particular value of t. It's not I'm not taking an expectation over there. So what is the property that is allowing me to do this? That's the line over there. T is conditionally independent of c given the confounding variables x. So once I condition it, if I extra give you the value of t, the conditional distribution does not change. Here, before I condition it, there may be a dependence between t and ct, but once I've conditioned on x, I don't have the relationship anymore. So, and from here to here, what happened? Here I just use the fact that once I condition on this, ct is equal to the outcome. And you get, in order to get the consistent estimator, what do you have to do? You have to look at all different values for which this x value could be there, the set of values of x in the population. You condition that xi is equal to xk, ti is equal to t, take the division of that. Basically you find an empirical estimate for this. The empirical estimate for that is the outer expectation is k going from 1 through nx, 1 over nx, which is the number of different values of x in the population. The inner expectation is basically this conditional expectation. The expectation of y, condition that t is equal to t and x is equal to xk. That's basically what the inner expectation is. All right. So at around 3 o'clock, these mosquitoes wake up, I think. Up until now, they are sleeping. All right. So what could potentially go wrong with this? So the story here is what we said was, this is something that if you go back into the website design problem, you're trying to say that you have some understanding of the age, the gender, the education level, and you think that their reaction to the website is going to, once you look at this, then the outcome, you have enough randomness within each cohort that if you randomly assign them to different categories, then t will be conditionally independent of the outcome variable. Where is this interference coming from? No, there's some interference happening with something. Okay. All right. So, returning back to this story. So what is happening here is that you're saying that there are some issues with this, which is These are called observational studies. This is something that traditionally people wanted to do, which is that whenever you're doing a study, you observe some demographics about these people, and then you say that within these demographics, the outcome, that is whether you put them into the treatment level or whether you put them in the no treatment level, the things are completely randomized, so there is no relationship between T and the outcome that you see. Within each group, you're randomly assigning people. But overall, there might still be dependence, but at least within each group, you're breaking them up. Now, when that happens, you have this tension that in order to get this conditional independence, you want to make this X as refined as possible, as small as possible, because in that set randomizing is easier. But then what will the cost that you pay in terms of this estimation? What will happen if I make X very refined? What will happen to my estimator here? What's likely to, I have to pay the cost somewhere. Things don't come for free. So if I make the things very refined, this conditional independence story becomes easy to do. But in terms of this estimator, where will I pay a cost? In the red part or the blue part? The red part is an average over the number of different values of X. That only increases. So what happens in the blue part? The number of respondents or the users that belong to each category starts to come down, which means that this conditional expectation versus doing this empirical estimate of the conditional expectation will have a high variance. And so you end up getting an unbiased estimator, but it will have a high variance. On the other hand, if you make this X large, then trying to randomize within that large cluster is going to become difficult. Because, for example, if you make the age cohort from 30 to 45, now if you think that 30 to 45 the people are exactly the same and you randomly assign them, if the incoming population was dominated by 30-year-olds and you randomly basically overweighted 30 people in one population and 45-year-old in another population, you will run into this trouble that if there was a confounding variable coming where age matters to what the outcome is, you will inadvertently cause a confounding factor, and you will end up into having the causal effect is not the same as the association effect. On the other hand, if you bucket it to 30 to 35, 35 to 40, 40 to 45, then the number of people that come into each bucket might become very small, which means that this variance will go up. So you'll have to balance the two. So there's a new technique that people have been using, which is called propensity scores. And here's where, so when nx becomes very large, the data gets very thinned, and as a result, the variation goes up. This is the place where machine learning has started to come and connecting with causality experiments. So let's, for the moment, define something called propensity, which is the probability that treatment is equal to T given that the confounding variable X is equal to little x. Okay? This is the probability a unit with covariate value X is assigned to treatment T. I don't do any randomization now. I somehow have this function at my control for the moment. We will figure out in a moment how do we get this. Whenever you have some conditional distribution, you should immediately start thinking in terms of a data analytic model. This is the outcome, the treatment level. This is the input, which is the various characteristics of this person, and we want to be able to see what happens to them. So let's look at this thing for a moment. The expected value of the indicator function that the treatment level is equal to T multiplied by the outcome in that condition Y divided by okay, there we go. The treatment level T and X. X is random, y is random, x is the random variable corresponding to that covariate value, y is the random outcome that you're going to get, t, I am fixing that treatment as equal to t. Again, I can arbitrarily just condition on these things, and now the outer expectation is over x, the inner expectation is a conditioned on x, so this is always true. Here I pull this qtx out. How can I do that? What happened over here? Why can I pull this function which was sitting inside and pulled it out? When I'm conditioning with respect to x, that x value is already known to me, so this is actually a deterministic quantity. When I'm conditioned on x, the denominator over here is a deterministic quantity because I know what it is, so I can pull it out. This outer expectation is still over x, so it's still okay, I'm just sitting it over here. Now how do I jump from there to there? Y is the outcome that I see for the various people, but when the treatment condition is equal to t, this y outcome is distributed according to ct. So that's the jump that you happen over there. What happened from over here to here? What happened from there to here? Here we use this property again, that t is conditionally independent of c given the confounding variable x. So if I look, this is a random variable that just depends on t, this is a random variable that depends on the treatment effects. They are independent, so the expected value of u v given x should be the same as expected value of u given x times the expected value of v given x, which is what has happened here. So it's a conditional independence that happens over there. Now this expected value is exactly equal to this probability. This expected value, the expected value of the indicator function t is equal to t given x, is exactly the probability that t is equal to t given x. So that quantity and that quantity cancel each other. What is left over is the expected value of ct given x, which is sitting here. The two expectations cancel each other, you get expected value of ct, which is mu t. Alright, so what happened in this whole drama? Why do I even care going through this whole exercise? We'll do it on the next slide, but I'm just trying to keep track of whether you guys went through this mathematical gymnastics, but keep track of what was going on behind it. So compare it to this story. We are in the same setting, right? We are in the setting where I have confounding variables such that t is conditionally independent of c given x. This is one possibility that I could do, which is I could divide up populations with respect to x, and then I take within each group the conditional expectation and then average over groups. And average over groups, that tells me one expectation. Over here, I did not divide it up at all. I just pooled everybody together. I just created this extra, a different estimator, a very different estimator compared to the estimator over here, and pooled everybody, took the expectation, and that expectation exactly equal to mu t that I'm after. So now the estimator that I can do is mu hat, which is all customers I going from 1 through n, indicator function ti equal t yi divided by qt xi. We did not have to stratify by x anymore. I did not have to divide up by people. I pooled everybody, and I'm hoping that by pooling everybody, my variance comes down. I don't have to divide up people, my variance comes down, and I'm hoping that I'm benefiting from it. Okay, but where do I pay the cost? I pay the cost because now I have to estimate this qtx. Nobody gives it to me. This propensity score, as it's called, is something that I need to compute. It's the probability that a unit with a covariate value x is assigned to treatment t. And that's a problem. So typically what people do is you fit this using some parametric model. You look at the treatment values, you look at the xi's, you construct some kind of a parametric model, you maximize it, and that will give you the qtx. And then wherever you have qtx, you put the maximum likelihood estimate theta hat and put them in. This can sometimes become unstable if this probability happens to be very small for some QTXI, but improved methods exist. So how do I want to connect up this story? What I'm doing right now is that up to this slide, causality seemed completely separate from data analytics. It is a separate idea. There is an idea which has to do with trying to understand how do I get causal estimates, and one idea that we had here was that within each, if I divide up things very narrowly, then within each group, if I randomly assign people, then I will get the causal answer that I'm after, and that's great. The next step that we did here is that we are now saying that if we have some way of accurately predicting how we are going to be assigning people of a particular cohort, then we can take advantage of that to be able to get a much better or much lower variance estimator. Okay. There are other ideas that one can do. We are going back to binary values t equals 0, 1. Yes?
On slide number 12.
Yeah.
That second last slide.
This one? Yeah.
I didn't got it. How did
So this one I use this fact. So let's say that you have 3 random variables x, y and z, and suppose I know that x is independent of y given z. So given z, x and y are independent. So let's first consider the case where x and y are independent. Then what is the expected value of x, y? We know that this is equal to the expected value of x times the expected value of y. If two things are independent, the expected value becomes the product, right? So now we are saying we are looking at expected value of y z or x y given z. But given z, x and y are independent. They are unconditionally not independent, but given z they are independent. So then I can write this as the expected value of x given z and the expected value of y given z.
My question was that how you cancel out qt with e.
Oh, the next one? Oh, this one to this one? Oh, that's from the definition.
Because it is probability, right?
Yeah.
And that is an expectation.
Yes. So if you have probability of any event A is the expectation of the indicator of that event, right? Because if the event happens, you'll get 1. If the event doesn't happen, so if you write this as an integral, suppose something like this. So this just becomes an integral over the event A of px dx, which is the probability. Where did we go? What happened to my here we go. There is an idea that has been around which has been, so the title here says matching using propensity scores, but really that part comes down here. There was an idea way before, which is when you just have two things, t is equal to 0 or 1. Matching is another technique. This was a comment that was made before by people. I think you made one of these comments. There are a variety of techniques to divide the data into pairs. Each pair consists of one treatment unit and one control unit. Each pair is similar on all confounding variables x. Similarity can be measured by the Mahalanobis distance and other kinds of distances that are available. So essentially what happens now is that you have one person that got the treatment, another person that didn't get the treatment. In reality, you want this person to be the same person. Same person got the treatment, same person did not get the treatment. But we can't do that. So we sort of say that the treatment is affected by these confounding variables x, and if I match two people on all these confounding variables and compare them, then I should get something which is a good measure of the causal effect. The problem is, again it's the same story. In order to get this independent story, we want to subdivide the population into smaller and smaller units. And we want to add as many confounding variables as I like, because that way I get this conditional independence property. But then the problem becomes high dimensional. And when you go in high dimensions, the probability that you will find two people that are similar or identical is going to be very difficult. So you run into most points cannot be matched. So you'll have to use a subset of points, and again, effectively you're paying the cost of variance. You had a population, you had to throw away most of it and drew an estimator based on a smaller set of population, you end up paying the cost of variance. So instead, this propensity score idea, one of the things this should have been not Q1x, meaning the treatment condition. So you use a one-dimensional propensity score. You can think of it as this is a dimension reduction problem. You have reduced the dimension from x, which is high dimensional, to one dimension, and the probabilistic assumption is t is conditionally independent of x given this q1x, given this propensity function. If you do that, you end up getting much better stories than what's going on over there. So that's one advantage of the propensity score, is that it really helps you reduce the variance in your estimator. But one of the problems with propensity score is that you end up having to, where did we go? We end up having to train this model. And if this model is bad, then propensity score matching is going to be bad. On the other hand, if we have made sufficient progress in machine learning and these models turn out to be pretty good, then our propensity scores are going to be good, and therefore I end up getting better causal estimates. And that's a direction that a lot of people are now thinking about. How do I go and hit these propensity scores using machine learning? Using maybe deep learning, which has very nonlinear classifiers. Because in this case, we often have fair bit of data available. So there's a lot of game that people are playing in this space. The next, there are a few more topics that I want to talk about, but this is a change in topic. So let's take a 15 minutes break now.